All right, let's dive into some Earth history.
Yeah.
Specifically, South America's wild ride back in the Cretaceous period.
It's a great story.
I mean, we're
Yeah.
talking dinosaurs, volcanoes,
Continents on the move.
and the clues are locked inside these ancient rocks.
The rocks themselves hold a record of Earth's magnetic field from millions of years ago. It's amazing.
We're talking paleomagnetism here, right?
Exactly.
So, okay, ancient rocks, magnetic fields, to track how South America moved around, specifically between 135 and 65 million years ago.
Yeah.
Okay, and
We're basing this deep dive mainly on a research paper that focused on mid-Cretaceous rocks in Patagonia's San Bernardo Fold Belt.
Patagonia, okay, so glaciers and mountains and all that.
Right, and within that fold belt, you've got these older mid-Cretaceous rocks, specifically the Castillo, Baja Boreal, and Laguna Palacios formations.
Those are the rock formations.
Yep, and these rocks are loaded with magnetite.
Which is a magnetic mineral.
Yeah, so basically these rocks become like magnetic time capsules.
Oh, I see.
And the researchers found something pretty interesting. The magnetic direction in these rocks. Remarkably consistent across different locations. So that tells us that the whole area moved as one block.
Oh, so they all stayed together.
Right, and didn't rotate much since the mid-Cretaceous.
So no dramatic spinning or twisting or anything?
Nope. So that's interesting in itself, but it gets even more interesting when we consider something called apparent polar wander.
Uh-oh, what is that?
Or APW. It's a bit of a misleading name
Okay.
because it's not the poles that wander, but the continents themselves.
Okay, how does that work?
Yeah.
How does a wandering continent, create this illusion of the poles wandering?
It's all about perspective. Think about it this way. Imagine you're on a ship sailing across the ocean.
Okay.
As you move, the stars appear to change position in the sky.
Right, but it's not the stars that are moving.
It's you. The ship is moving. So from the continent's perspective, it's like the magnetic poles are shifting, but it's actually the continent that's doing the moving.
Ah, I get it. So by studying these apparent shifts in the poles, we can trace these historical journeys of the continents, right?
Exactly. And when researchers applied this to South America, they found something fascinating. Between 125 and 100 million years ago, South America stood relatively still, like pause button.
A pause button, wow.
So it wasn't this constant drifting. There were periods of stability.
But I'm guessing this pause didn't last forever.
Nope. Things got interesting again between 175 million years ago when South America decided to head south.
Okay.
And this southward drift coincided with a major shift in the Andes.
Oh, the Andes Mountains.
Those majestic mountains running down South America's west side. Are you saying that South America's movement actually shaped the Andes?
Yeah, how does that even work?
It's all about tectonic regimes. These are basically the styles of forces that act on the Earth's crust.
Okay.
Before the southward drift, the Andes were experiencing extension. Picture like a rubber band being pulled apart.
Huh?
But then things changed.
Because South America started moving south.
Exactly. And those forces shifted to compression. So picture it more like two cars colliding head-on.
So South America's southward drift basically created a continental car crash that built up the Andes.
And we're just getting started. There's actually a whole other layer to this story, a bit of a geological controversy that throws a wrench into things.
Okay, now you've got my attention. A controversy.
It's all about the idea of true polar wander. So imagine, instead of the continents moving, the entire Earth tilts on its axis. A cosmic wobble, you could say?
Whoa, a whole planet tilt. That sounds dramatic. How do scientists even study something like that?
They use what we call hotspots as reference points. Think of it like plumes of superheated material.
Coming up from deep inside the Earth.
Yeah, like torches.
So they're kind of like landmarks.
That's the idea. But there's a catch. Scientists try to reconcile the paleomagnetic data from South America with the positions suggested by hotspots, and what did they find? A mismatch.
A mismatch.
Yeah.
So the continents weren't where the hotspots said they should be?
Exactly.
So does that mean the Earth actually tilted?
That's the big question.
I can't wait to hear more.
The paper we're looking at suggests that the mismatch might point to something even more intriguing. It might challenge the whole idea of hotspots being fixed markers.
Wait, are you telling me that these hotspots, these giant torches, can move?
It adds another layer of complexity.
And makes the story even more fascinating.
No, you're right. It's about to get really interesting. By understanding how these hotspots move, we can get a much more accurate picture of South America's journey and maybe uncover a few surprises along the way. Welcome back. Before we jump into those moving hotspots, I want to touch on something you mentioned earlier.
Oh, what's that?
You asked how South America's movements shaped the Andes.
Yeah, it's hard to picture, like, how continental drift created these massive mountains.
Right. It's like imagining the slow motion collision, but on this giant scale.
Yeah.
And that's exactly what it is, a slow motion collision. The Andes are a perfect example of how plate tectonics can create these dramatic landscapes. And those tectonic regimes we talked about, they play a key role.
Okay, remind me about those again.
Sure. So we talked about extension and compression, right? Think of it like this. Extension, it's like pulling a piece of dough apart. It stretches, it thins.
Huh?
That's what was happening in the Andes early on. But then, when South America started drifting south and then accelerating westward,
It created that compression force,
exactly, like pushing the two sides of the dough together.
which pushes it upwards, building the mountains.
You got it. And the research suggests that this Andean uplift wasn't just one single event.
Oh, so it happened in stages.
Yeah, think of it like waves crashing on a shore, each one pushing the land up a little bit higher.
So the Andes were built up in pulses, driven by these shifts in South America's movement.
Exactly. And this is one of the exciting things about geology, Everything's connected, but those connections aren't always obvious.
Right. And speaking of connections, let's go back to those moving hotspots.
Yeah, those fixed markers. That might not be so fixed after all.
Right. So how does this change our whole understanding of South America's journey?
Well, if we don't account for the fact that hotspots can move, our reconstruction of where continents were could be way off.
It's like trying to use a map where all the landmarks keep jumping around.
Exactly. So scientists have come up with something called a moving hotspot reference frame.
Okay.
It takes into account that these hotspots can actually drift over millions of years. So you're not just tracking the continents, but also these hotspots themselves, like a bunch of dancers moving around.
Well, I like that.
So instead of just saying, okay, this continent should be here based on this hotspot, you have to factor in this whole other layer of movement.
That's complicated.
It is. But it gives us a much more accurate, more dynamic view of the past.
So what did we learn by using this moving hotspot lens?
Yeah.
Did it confirm what we already knew about those periods of stability and movement?
Absolutely. It confirmed that, yes, South America did experience that stillness.
From about 125 to 100 million years ago.
Yeah. And what's even more interesting is that during the same period, North America was also experiencing a standstill.
Wait, so both North and South America were taking a break at the same time?
Yeah.
Is that just a coincidence?
Could be. Some theories suggest that it might be connected to larger global shifts, maybe changes in mantle convection patterns, or even a slowdown in plate tectonics.
So this seemingly quiet period for South America could actually hold clues to, like global changes happening deep inside the Earth.
It's fascinating, right? And that's what makes studying geology so captivating.
Yeah. Even these periods that seem still can tell us so much.
Now, after this pause, remember how South America started drifting south and then really accelerating westward?
Yeah, that's what helped build the Andes, right?
Exactly. But looking through this moving hotspot framework, it gives us a more nuanced view of that whole movement.
So it wasn't just a smooth drift south and then a sharp turn west.
Not quite. These movements were more complex, with all sorts of variations in speed and direction over time.
And those variations would have affected the Andes.
Absolutely. So instead of this steady, continuous mountain building, it was more like this dynamic dance.
With those pulses of uplift we talked about.
You got it. It's like a sculptor working with clay, constantly shaping and reshaping it. The Andes were formed through this kind of back and forth, influenced by these shifts in plate movements and the hotspots.
Wow. And to think we're talking about events that happened over millions of years at a scale that's just hard to even imagine.
I know, right? It's amazing. But we can study these rocks, these magnetic fields, and start to understand these massive processes.
It's pretty powerful.
It is. And there's another twist to the story. Around 95 million years ago, there was this major plate reorganization.
Oh, okay, here we go again. What happened?
It was like someone shook up the whole tectonic puzzle. Plates shifted, they collided, they broke apart in new ways.
A global tectonic shakeup. Sounds intense.
It was. And this event actually marked the final separation of South America from Africa.
So they finally parted ways.
Yeah, after millions of years together. And this was huge for South America. It allowed the South Atlantic Ocean to fully open up, and it set the stage for that westward acceleration we've been talking about.
It's amazing how one event can have these ripple effects, across the whole globe.
I know, right?
So how does this plate reorganization tie back to those hotspots? Did it cause them to shift as well?
That's a great question. It's something that geologists are still trying to figure out. But there is some evidence that suggests that these major plate reorganizations can actually influence hotspot behavior.
So this tectonic shakeup might have sent shockwaves through the Earth's interior, nudging those wandering hotspots in new directions.
It's possible. Imagine the Earth's mantle like a vast ocean, with currents and eddies swirling around these major plate movements. They could create disturbances in those flows, potentially affecting those rising plumes.
This is all so incredible. We started with studying these rocks in Patagonia,
Right.
and now we're talking about this global event that impacted continents and oceans all over the planet.
And we're just scratching the surface. There's still so much more to learn about this plate reorganization, how it impacted those hotspots, and the role it played in shaping our world.
It's such an incredible journey, and it's clear we're only at the beginning of understanding this complex, dynamic history of our planet.
Absolutely. There are so many more mysteries to unravel.
So we've got this massive plate reorganization that happened about 95 million years ago.
Yeah.
A real game changer, but it sounds like it's also incredibly complex to study.
Oh, it is, especially when we try to understand how it affected those hotspots. One of the biggest challenges is the fragmented geological record.
Ah, so like missing pieces of the puzzle.
Exactly, especially for the oceans. Imagine trying to put together a shattered vase, but you only have a few pieces.
It's going to be frustrating for geologists.
It is. But luckily, we have new technologies that are helping us fill in those gaps. Things like seismic imaging.
What is that?
It's like an X-ray of the planet, so we can see what's going on deep inside.
Oh, wow. So we're getting a better look at the mantle.
Yeah. And what we're learning is that the mantle plays a huge role in driving these tectonic processes. And it looks like hotspots might not all be created equal.
What do you mean?
Well, some hotspots seem to be pretty stable over millions of years, but others are more mobile.
Oh, so they're drifting around too.
Exactly. And that just adds another layer of complexity to the whole system.
So it's like a giant dance with everything moving around.
It is. And researchers are particularly interested in these large-scale mantle plumes.
Mantle plumes, what are those?
Think of them like giant chimneys that channel hot material from deep inside the Earth
Oh, okay.
all the way up to the surface. These plumes are thought to be what drives many hotspots. So the hotspot is kind of like the tip of the iceberg.
And the plume is the massive force underneath.
Exactly. And here's where it gets really interesting. Some scientists think that these plumes might actually be what triggers these major plate reorganizations.
Hold on, are you saying that plumes rising up from deep inside the Earth could be powerful enough to, like, reshape continents and oceans?
It's a pretty compelling idea. Imagine a plume head, this massive blob of hot material reaching the bottom of the Earth's crust. That influx of heat could weaken the crust, causing it to break apart.
And that could create new plate boundaries.
Yeah, and then set off this cascade of tectonic events. So it's like a chain reaction, starting deep down and rippling outwards.
Wow. So could this explain that reorganization that happened around 95 million years ago?
Some researchers think so.
This is amazing. We've gone from rocks in Patagonia to plumes deep inside the Earth, and it's all connected.
Right. It's all part of this incredible story.
And it shows just how powerful and dynamic our planet is.
Absolutely. But let's bring it back to South America and the Andes for a moment.
Okay, yeah. What did this research tell us about what happened there specifically?
Well, it showed how those changes in South America's movement played a huge role in shaping those mountains.
Those shifts in speed and direction and those periods of stability, it all had an impact.
Yeah. Think about it. When the South Atlantic was opening up, there was a lot of extension in the Andes region.
Right. The crust was being stretched and thinned.
But then, as South America accelerated westward, those forces switched to compression.
And that's what built up the Andes.
It squeezed the crust together, pushing it upwards to create those towering peaks. And the Andes are still evolving today, you know?
Oh, wow.
They're a constant reminder that our planet is a dynamic system, constantly changing.
This deep dive has been incredible. We've covered so much, from magnetic rocks to these massive mantle plumes.
It's been a fascinating journey.
I feel like I've learned so much about how our planet works.
And I hope our listeners feel the same way.
It's just a reminder that there are so many secrets still waiting to be discovered.
Exactly. And who knows what amazing discoveries are out there just waiting for us to uncover them.
Well, that's all the time we have for this deep dive. Thanks for joining us on this incredible journey through South America's past.
It's been a pleasure.
And we'll be back soon with another exciting exploration of the world around us. Until then, keep those minds curious.